Welcome to this presentation on step response. This is also a very important topic. The outline is as follows. We will derive an expression for step response. We will derive it from impulse response, and vice versa. We will derive impulse response from step response. We will point out the importance of step response. What is step response? We define it now. For an LTI system, so this is for linear time invariant system, at 0 initial state, this is extremely important. Remember, if it is not 0, the system is not linear from input output perspective. With a unit step input, so we call it step response, that is u of n equals 1 of n. Remember, we are using the symbol 1 of n to denote unit step. This is the input signal that takes the value 1 of n. Remember, the braces mean it is a doubly infinite sequence. 1 of n is unit step, that is it has zeros all the way until n equals 0. From n equals 0 onwards, it takes the value 1. The output for this input is defined as the unit step response and also abbreviated as step response. We will use the symbol S of n for this. In fact, this S of n is reserved to denote step response or unit step response, just like G of n is reserved for impulse response. Let us recall the convolution expression for output. Here is this infinite sum. Let us now substitute u from this formula, and remember that we are calling that as S of n. Let us substitute here. Summation remains the same. In the place of u of k, we put 1 of k, g of n minus k. Of course, some simplifications are possible, which we will see in the next slide. Okay, what simplifications? First of all, notice that we have 1 of k. So let us use the meaning. It says that this is non-zero only from k equals 0 onwards, before that it is 0, and the non-zero value is 1, so we do not have to write that. Non-zero from k equals 0 onwards, so we write this k equals 0 to infinity, we get this expression. That is, the step response is a sum of impulse responses. Remember, this is the impulse response, that is how this G is defined. This is the step response. So the step response is obtained as the sum of impulse responses. Let us see an example. If G of n is given here, what is the step response? So let us use this formula, and now let us substitute for G of n minus k. So go here and substitute n minus k wherever n occurs. We can simplify further because now it is 1 of n minus k, and this k cannot, when k exceeds n, that is when the argument becomes negative, it will become 0. So we can say that we need to consider only up to n, and this is valid only for n greater or equal to 0. So as a result, I can pull out this 1 of n and I get this expression. Now let me call n minus k as r. So in the place of k equals 0, I get r equals n, and I get 0 here. Now it is easy to evaluate this. Of course, I write it as r equals 0 to n. Then this is a sum of geometric terms, geometric progression. So I apply this formula, and in the denominator we have 1 minus 0.5, numerator 1 minus 0.5 to the power n plus 1. So in the denominator I have 0.5, I divide out, 1 by 0.5 is 2. When I divide this, one of the powers goes away, I get 0.5 to the power n, I get 1 of n. We will come back to this problem once again in a future presentation, but this is the step response that we wanted to calculate. We saw two responses, one is an impulse response, the other is a step response. Is there any relation between them? Recall the expression for step response, it is given here, that is the step response is the sum of impulse response. This is not surprising, the fact that we got step response as a function of impulse response is not at all surprising, because impulse response has all information about the system, we already saw this. So naturally we can express any arbitrary response to any arbitrary input as a function of impulse response. So we can get the response to a step also as a function of this. Okay. Of course we have got a specific expression, namely it is just the sum, but that it is a function of impulse response is not at all surprising. So we can construct step response from impulse response, but what is surprising is that step response also is special. So that we will see in the next slide. It turns out that we can get impulse response from step response. How do we show that? Recall the fact that we derived in one of the earlier presentations. Delta of n is 1 of n minus 1 of n minus 1. This is the step that starts at n equals 0. This is a step that starts at n equals 1. Now let us use linearity and time invariance. So this 1 of n will give rise to S of n. When 1 of n minus 1 is used, we get S of n minus 1 to the same system, and we use the same S because it is time invariant. If it is not time invariant, I cannot use the same S, and because it is linear, I can use the same combination for the S. So 1 of n produces S of n, 1 of n minus 1 produces S of n minus 1. I use the same S, otherwise I use the same S because it is time invariant. I use the same combination, namely this is subtracted, I subtract this also because it is linear, and this is G of n. I give this delta of n, I get this output G of n. I give this 1 of n, I get the output S of n. I give this 1 of n minus 1, I get this S of n minus 1, and we have derived the result, that is G of n is S of n minus S of n minus 1. This says that given a step response, one can find impulse response. Okay. Given step response, you can find impulse response. Recall that the only experiment you have to do is S of n, that is you have a system, linear time invariant system, initially at rest, and you give the step that starts from n equals 0 onwards. You measure that output, you call it S of n. Do you have to do this experiment? How do you get S of n minus 1? Well, you do not have to do that experiment once again, because it is the same n, same S, but time shifted by 1, that is it. So given this S of n, you can actually find out what S of n minus 1 is just by shifting it by 1. So this S of n has all information about the system, because given S of n, you can get S of n minus 1, and from that you can get G of n. G of n has all information about the system, that is the impulse response has all information about the system, which itself can be determined from S of n. So we say that S of n has all information about the system, that is the step response has all information about the system. Step response has all information about the system, so one can calculate the response to an arbitrary input to the step response, right. Because step response has all information, the response to any arbitrary input can also be calculated. You do not have to do any more experiment. This is the only experiment that is required. That is the only experiment you ever need to do. That is the importance of step response. Okay, there is no need to do any more experiment. So we made a similar statement while introducing the impulse response also. Okay, we considered step response, we considered impulse response. In fact, we derived both of them. Both of them have all information about the system. Is any one better than the other? It turns out that the step response is more useful in practice. What is it? In general, it is difficult to generate an impulse signal. Why? Imagine generating a signal that is 1 at exactly one instant and 0 elsewhere. This becomes difficult, especially when the sampling frequency is very high. The time gap between two samples is very small, of the order of seconds, if not milliseconds or nanoseconds. The smaller the sampling time, the more difficult it is to generate an impulse signal. It is easier to generate a step signal, at least approximately. So because of that, we say that the step response is more useful in practice. For theoretical calculations, of course, given step response, you can always determine impulse response, as we explained earlier. That brings us to the end of this presentation. This is a very important topic. I would urge you to go through this and understand it well. Thanks for joining.